Hello, and today we're going through differentiation, the whole topic, but we're just going through the content, so we're not going to do any questions. So let's get started. So first, let's start with the basics. So dy over dx is just equal to the gradient. And to find the gradient of a graph at any point, you can just draw a tangent and find the change in y over the change in x. And the change in y over change in x is just equal to the gradient of that point of the curve. And to do differentiation to find dy over dx, if you have a function of y that looks something like this, y is equal to axn, to differentiate it, you will get a times n times x to the power of n minus 1. So you would multiply the power by the constant or by the coefficient, and then subtract the power by 1. Now let's move on to finding an equation of a tangent and a normal. So first, imagine we have a point x1, y1, like this. And we're trying to find the equation of the tangent and the normal of the curve at the point of x1, y1. And to find the gradient of the tangent, so m tangent, we would do dy over dx of the curve, and then substitute our value of x1 into the dy of dx to find the gradient. And then for the equation of the normal, we would just do the negative reciprocal of the equation of the gradient of the tangent. And then from here you can find the equation of the curve by substituting into y equals mx plus c, and substitute your values for x and y into the equation to find c, and then you'll have an equation in terms of x and y knowing m and c. Or you could alternatively substitute it into this format, x minus x1, and you can substitute your values of x1, y1 into these two places, and then you will still get an equation of a line. You just need to rearrange it to the form y equals mx plus c to make it look like this. So now let's move on to increasing and decreasing functions. So an increasing function is when the gradient is at least 0 for all values of x. So we can write it. So dy over dx is our gradient. So dy over dx, which we can write as f dash x, which is greater than equal to 0 at for all values of x. And for strictly increasing, we would have f dash x is greater than, not equal to 0 for all values of x. And this is for increasing. So this would be an increasing function, and this would be a strictly increasing function. And for a decreasing function, you would just have f dash x, so the gradient of x is smaller than or equal to 0, and for strictly decreasing, f dash x is less than 0. Now, if you have a function which can be both increasing and decreasing, to find a range of values for which that some parts are increasing and some parts are decreasing, you would just do the derivative x. Whatever parts of the graph are greater than 0, or the gradient is greater than 0, then this part is increasing. And if you have f dash x, which is smaller than or equal to 0, these parts of the graph are decreasing. So say now you have a quadratic in the form of y is equal to ax squared plus bx plus c, and you're trying to prove that all the values are increasing. So how would you do this? So first you would complete the square, so you would be left with a form something like this. And if your f value is positive, then this is an increasing function, because this value squared is going to always be positive. So if this is positive and this is positive, the value of y will always be positive, because this is equal to y. Now let's move on to turning points. So if we look at how turning points look like on a graph, we would have something like this, something like this, etc., right? And the turning point is when the gradient of the graph at each of these points is 0. So dy over dx is equal to 0. So to find which points are the turning points, you can just differentiate your function like this and make it equal to 0 and solve for your x values. And then once you find x, then you can find y. And there's 3 different types of turning points. So you either have a maximum, which looks like something like this, and you have an increasing gradient, then a flat gradient, and then a negative gradient. And so you have a positive gradient, then negative, then zero, then negative. A minimum point looks something like this, where you would have a negative gradient, then a zero gradient, and then a positive gradient. So you would have negative to zero to positive of the gradient. And then you'll have an inflection. And there's two different types of inflections. You either have one that looks something like this, or one that looks something like this, where you would start off with a positive gradient, then zero gradient, then positive, then you'll have negative gradient, zero gradient, and then negative again. So you would go from either positive to zero to positive, or negative to zero to negative. And these are all the types of turning points. Now let's move on to the second derivative. So the second derivative is dy over dx. So to get dy over dx, you would just do d over dx. So differentiate your value for y, so your function. And to get the second derivative, you would just do d over dx of your dy over dx. So you would differentiate twice the function. So, and this can be written as f dash dash x, or you can write it as f squared y over dx squared, like this. And this is very useful to find what type of stationary point you have. So say you find that your dy over dx is equal to 0. That means you have a stationary point there. And to find a type of stationary point, at that point, so your x value, you differentiate twice, the equation twice, so you get d squared y over dx squared. And then you substitute your value for x inside. And if your value for the second derivative is greater than 0, then this is a minimum. If your d squared y over dx squared is smaller than 0 at this point, it would be a maximum gradient. And for inflections, you would have d squared y over dx squared is equal to 0. However, you would have to check that values next to, say you have your x1, point x1, you would have to check your x1 minus 0.1 and your x1 plus 0.1 to check how the gradient looks like. And you will substitute this into your dy over dx to find the gradient. So you can find whether it's positive to 0 to positive, or negative to 0 to negative, to confirm that it's a inflection point. Now let's move on to optimization problems. So for optimization problems, let's do an example. Imagine you have a cuboid. So it would look something like this, but this is actually a square prism because you have x here, which is the same length, this height here, and the length would be equal to a y. And if you are told that the surface area is equal to 54 meters cubed, how would you find the maximum volume of the shape? And this is not optimization problem. We're going to go through every step, and you can repeat these steps for different types of questions. So let's start with the first step. For the first step, we would use our equation for the surface area, which we can write as, so we'll have the surface here, so this surface, and then we have the same on the other side. So we'll do x squared, which is the area of the square, plus x squared, because we have another square on the other side, on this side. So we have two squares here. So that's some surface area. Then we would have plus x times y to get the area of this. And then we'll multiply it by 4 times because we have this area here, the one at the back, and the one below it. So we would have 4xy. And this will be equal to our surface area. Using the surface area, we would substitute our value, which they said was 54. So if we do 54 is equal to, then we can just join these two together. We'll get 2x squared plus 4xy. And once we get this, we can make y the subject. So let's rearrange this equation. And now we have the rearranged version of it. So now what we would do is make an equation for the volume. So step 2 would be make an equation for the volume, and we can say the volume is equal to x squared y. And now, since we have a value for y, we can just substitute it into the volume equation, and we would have v is equal to x squared times this whole expression, which we have in terms of x. And if you expand this out, you would get something that looks, so we'll expand this out slowly. We'll get 54x squared at the top minus 2x to the power 4 all over 4x, which we can rearrange to get 54 over 4x minus 1 over 2 x cubed. Now in the third step, what we can do, differentiate in terms of x, so we'll have dv over dx, which is equal to 54 over 4, because we reduce the power by 1 and multiply it by the power, which is 1, minus 2.5 times 3, which will be 3 over 2. And then we will reduce the power to get squared. So this is dv over dx. And we will know that the maximum or the minimum, so we're looking for the maximum, and we'll know the point of the maximum, we would have a 0 gradient like this. So we'll just make this equal to 0. And now, if we solve for x, we'll get 54 over 4 is equal to 3 over 2 x squared. And if we rearrange that, we would get x squared is equal to 9. So you would get a plus minus 3 is equal to your x. So we would have two values for a stationary point. One could be a maximum and one could be a minimum. Now, if we substitute back into the equation of v, so the next step, step 4, would be to substitute our values for x into our equation that we got for v in terms of x, which is this one, and see what we get. So if we do 54 over 4 times plus minus 3 minus a half plus minus 3 to the power of 3, we would get our v's as 27 or minus 27. And which one is larger between these two? It's obviously the 27. And because you can't have a negative volume, so we'll see that the maximum volume would be equal to 27. Now, what we would do to check if it's a maximum, we would do the second derivative. So we know that our v is equal to 27, and our dv over dx was equal to 54 over 4 minus 3 over 2 x squared. If we differentiate this one more time, the 54 over 4 will disappear, and we'll be left with minus 6 over 2 x, which is equal to minus 3x. And if we substitute our value for 27 into the equation, so our d squared v over dx squared is equal to minus 327, which we know already because of the negative sign is less than 0, therefore it is a maximum. So we have proved that the maximum volume you can get is 27. Let's recap on all the steps we've done so far. So they can give you either equations of, they can give you either surface area as a function of x and another value h, in this case it was y, or they could give you the volume as a function of x in terms of h, with the same thing. And now you would substitute, rearrange the equation to get h is equal to a function g, or in terms of x and your surface area or your volume. So this would be your first step, this would be your second step. Your third step would be to substitute h into another equation. So say you have your surface area and you're trying to find your maximum or minimum volume, you substitute into the volume equation. And if you have your volume, you'll substitute into the surface area equation. So you would get another function a, for example. So you would have volume is equal to a function a of, in terms of x, and your surface area, or your surface area as a function a of x and the volume. And once you do this, your step 4 would be to find the derivative and make it equal to 0. So you would do either dv over dx is equal to 0, or your d of your surface area over dx and make it equal to 0. So step 5 is to solve for x. And then step 6 is find the second derivative to find the nature of the stationary point. And these are all the steps for optimization problems. And if you want to just look back through the question we just did, it would be good practice to just try different values and try, instead of surface area at the start, you try to maximize the surface area given a volume and stuff like that. Now let's go on to sketching gradient graphs. So say if you have a normal function f of x is equal to y. To find the gradient function, you will just do dy over dx is equal to f dash x, for example. And once you find your f dash x, you can just choose values for like 0, 1, 2, 3, etc. And you can go in the negative direction, 0, minus 1, minus 2, minus 3, etc. And for these, you can just, once you know the gradient and find your gradient for each of these points, and once you find the gradient for each one of these points, you can plot a graph which looks something like this of gradient on the y-axis, so f dash x on the y-axis, and your x values on the x-axis, so like this. And say you have a graph that looks something like this. So how would we plot the gradient? So first we would find all the gradients at each point. So say at 0, we see that our gradient is positive because we're going up like this. So we would plot it like this. And in the real exam, you'll find that exact gradient and plot the point on the y graph. And then you realize here at this point, you'll have increasing gradient as well. It'll be positive, but it's less positive as it's curving downwards. So you have a point over here, not as positive, but it's still positive. It's still above the x-axis for the gradient function. And then here is less positive, and then here it becomes 0. So at this point, it will be 0. And then here it starts to become negative. So the value of the gradient will be below the x-axis. And then the same for this side, you will have positive gradient at the start, but it becomes less positive. And then it just becomes negative at this part here because it goes down like this. So you have something like this. And if you were to draw it, you would get something like this. And does this fit with the shape of the graph? So say if this one looks very similar to a cubic. So you have f of x is around a cubic. So we can just say, assume it's a cubic. And if we differentiate this, f of dash x would be 3x squared. So it would be basically a quadratic. And does that look like it? Yeah, this does look like a quadratic function, even though my drawing is quite bad. So this is how you draw a gradient function on the graph. Now let's go on to first principles. So here you just have to know a formula, which is f dash x is equal to the limit h is equal to 0. We're going to explain what this means in a second. And then you have a fraction of f of x plus h minus f of x all over h. So because you can't have a value over 0, you'll get infinity. So that's why h tends to 0. So to find the derivative of function f of x, you would put a function like say x squared into here, and then here you would get x plus h all squared because your function is x squared all over h. We can try it for this example. So if we're trying to find the derivative of x squared, we can substitute into this formula and we would get limit h is equal to 0, x plus h all squared minus x squared over h. And we can rearrange this. We can expand out the brackets over here. And we would get x squared plus 2hx plus h squared minus x squared all over h. And remember this to apply your limit down here. And because the x squared and x squared cancel out, you would get 2hx plus h squared over h, which can be simplified into 2x plus h. And now, if we tend h to 0, we can just substitute h as 0, and we would get 2x. And this is our derivative for x squared. And now let's go on to year 2 content for differentiation, shapes of curves. So in a curve, we either have an increasing gradient or we have a decreasing gradient. An increasing gradient would have a graph which looks something like this. And this we would call concave upwards or convex downwards. And for a decreasing gradient, we will have something that looks like this. And we would call this concave downwards or convex upwards. And the convention is to use the down. So if they say convex, you would just assume it's convex down. And if they say concave, you would assume it's concave down. So the yellow is the convention. Now let's go on to the chain rule, and this is used to differentiate composite functions, which look something like this, where you have a function of another function. So f of g of x, for example, say if you have something like this, dy over dx is equal to f dash of g of x multiplied by g of x dash. And this can be written as dy over dx is equal to dy over du times du over dx, where in this case your u would be g of x. So you can write a function instead like this, f of u instead of g of x, and if you do dy over du, you'll do dy over du, which is basically this term over here, f dash of g of x. And if you do du over dx, this is basically the same as differentiating g of x by itself. And when you multiply them together, you'll get dy over dx. And now let's go on to connected rates of change. A prerequisite for connected range of rates of change would be, it's really useful to know that if you have a gradient y in terms of x, so you have y here and x here, and then you've got another graph that looks something like this, and then you've got x and y instead. If you have a gradient that is like this, it would be the same as doing a gradient like that. So it's the same gradient, but just y and x are just in different places. What can we tell from this? We can tell that y dy over dx is the same as 1 over dx over dy. And this is very useful for connected rates of change. And this can be proved using the chain rule. So dy over dy is equal to dy over dx times dx over dy. And if you dy over dy would just be 1, so you can just rearrange and you would get 1 is equal to dy over dx times dx over dy, because each of these will cancel out, so the dx will cancel out and you will leave the dy's, so you get dy over dy. And then if you rearrange, you would get 1 over dx over dy is equal to dy over dx, just like the formula from before. And now let's go on to a connected rates of change. So we're going to do an example, and then we're going to go through all the steps for all the examples, and you can just apply these steps to any other example. So we have a spherical balloon is inflated at 150 centimeters cubed per second. Find the rate of change of surface area when the radius is 6 centimeters. So how would we start off with this question? First, we would start off with the fact that we know that dv over dt is equal to 150 centimeters cubed per second. And using this chain rule, the chain rule that we did before, and using connected rates of change, we can make a equation of the rate of change of surface area, which is what they asked for in the question. So we can say this is dA over dt, which you can write as dA over dV times dV over dt. Because the dV's cancel out, and you'll be left with dA over dt. So to find dA over dt, first we need to find dV over dt, which we just found, so which is 150, and our dA over dV, which we can find using a different equation, so dA over dV can be equal to dA over dr, because we can find easily an equation of a surface area in terms of the radius, and then we can multiply this by dr over dV, which is also easy to find a equation of the volume in terms of the radius, because it's a spherical balloon. And we know that the surface area of a sphere is equal to 4 pi r squared. So dA over dr, if we differentiate this formula, we would get 8 pi r, like that. And now we found dA of dr. Now to find dr over dV, we can find easily dV over dr. So V is equal to 4 over 3 pi r cubed for a sphere. And we can find dV over dr very simply by just differentiating this. And we're going to get 4 pi r squared. So now to find dr over dV, we can just use the formula from before, the 1 over formula, this one over here. And we can find that dr over dV is just going to be 1 over dV over dr. So we can express this as 1 over 4 pi r squared. Now we have these two values, we can find dA over dr. We can get dA over dV is equal to dA over dr, which is 8 pi r, times dr over dV, which is 1 over 4 pi r squared. And this is equal to 2 over r. Now we have our value for dA over dV and dV over dt, because they gave us dV over dt, and now we know dA over dV, which is 2 over r, and they are asking for when the radius is 6 centimeters. So if we substitute r as 6, we'll do 2 over 6 multiplied by 1 over 50 in this equation, which is dA over dV, which is 2 over 6, and dV over dt, which is 150, we would get 50. So the rate of change of the surface area in terms of time is 50 centimeters squared, because it's area, per second, and that's how you get it. And if we were to recap and how we would apply this to different formulas, just remember to use the chain rule like this to try to get your desired result, and you can use it as many times as you need. And remember this formula over here, so it's good to use the chain rule or the formula we said before, which is 1 over dx over dy is equal to dy over dx. So these two formulas are very useful for connected rates of change. Now let's move on to formulas for 3D shapes, which are also very useful for connected rates of change, because you can use them. And we'll just go through all the formulas that you will need to know for the exam, as we use them for this question quite a lot for the surface area and the volumes. So let's go through all the formulas you would need to know for the exam. So first you would have a sphere. So the volume of a sphere was 4 over 3 pi r cubed. The surface area of the sphere is equal to 4 pi r squared. So now the equations of the cylinder, the volume is equal to pi r squared times the height, and the surface area is equal to 2 pi r squared. So the two areas of the circle plus the 2 pi r h, which is the area of the round part of the cylinder. So for a cone, the equations would be volume is equal to 1/3 times the pi r squared h, and the area of the curved surface of the cone is equal to pi r l. And you can just, for the surface area, total surface area, you would add the circle part of the cone. We're going to draw the diagrams after. So now let's draw what each of these mean for each of the equations. So for a cone, say you have a cone that looks something like this. So the height of the cone would be this part here. The radius would be this part here. And the length would be this part here. And for a sphere, you would have something that looks like this. And the radius would just be from the center to the edge. And for a cylinder, you would have two circles, one at the top and one at the bottom, connected like this, where this is the height and this is the radius. And then we get all these equations. Now let's move on to the product rule. So the product rule is to differentiate a function where you have two functions, y is equal to f of x times another function, g of x, which you can write as y is equal to u v, where f of x can be u and g of x is v. And you can write this out as dy over dx is equal to u times dv over dx plus v du over dx, which can be also written as the whole function, which we can call a of x. The differential of a, the function a, is equal to f of x times the differentiation of g of x plus the function g of x times the differentiation of f of x. And these are the two. This is the product rule. It can be written like this or like this. Now let's move on to the quotient rule. So the quotient rule is used when you have y is equal to a function that looks like this, u over v, which can be written as, say, f of x all over g of x. And here, the equation for the differentiation, dy over dx, is equal to v du over dx minus u dv over dx all over v squared, which you can write as well as, so this is, say, another a of x. So a of dash x is equal to v, which is g of x, times the differentiation of f of x minus f of x times the differentiation of g of x all over g of x. And this is only when you have f of x at the top and g of x at the bottom. So you can write the equation like this or like this, whichever one helps you understand it better. And these are the two equations. So now let's move on to differentiating exponentials and logarithms. So say we have a function which we can call f of x. If we want to differentiate this, we can just apply this function like this, d over dx, and we'll get f dash x. So if I use this function over here, just remember it just means differentiating this into a differential. And so now let's apply this to exponential and logarithm functions. So if we differentiate d over dx of e of kx, we would get k of e kx. If we differentiate d over dx of ln, so the natural logarithm of x, we would get 1 over x. And now, if we differentiate an exponential that isn't e, dx of e, which is the natural exponential, if we have a different one, so say a, any constant a to the power of x, is equal to ln, the natural logarithm of a, multiplied by a to the x. And if we differentiate a to the kx, we would get k times ln, the natural logarithm a, multiplied by a to the kx. And these are differentiation for exponentials over here and a logarithm. Now, if you want to differentiate trigonometric functions, for example, sine and cos, this is very simple to remember. So say we start off with sine x. If we want to differentiate sine x, so d over dx, as we said before, we will get cos x. And if we get cos x and we want to differentiate cos x, we'll get minus sine x. And because this is a constant in front, the negative is a constant in front, we can repeat this and we'll get, say, differentiating the sine x, which becomes cos x multiplied by minus 1. So we'll get minus cos x. And this will repeat and we'll get sine x again, because that is if you differentiate the cos, you get minus sine times minus 1, you would get positive. And this, as you can see, we have started from the beginning and the cycle will repeat. And if you want to integrate, this is just an extra, to integrate, you just go up, which is the opposite of the differentiation. It's just bonus for today. So this cycle repeats on and on and on. Now for sine and cos, there's a special case of the chain rules, that if you differentiate d over dx of any value of sine with a constant times x inside the brackets, you'll just get k, which is the differentiation of the kx in the middle, and then times sine kx inside the brackets still. And this still applies for cos as well. So if you differentiate cos with kx in the brackets, you'll get k, the constant, which is the differentiation of the inside of the brackets, times minus sine, which will become minus k, sine kx, all inside the brackets. Oh, sorry, this will become cos because sine differentiates into cos. Now let's go on to implicit differentiation. And this is when you're trying to differentiate d over dx of a function of y. So what we can do is just f of dash y multiplied by dy over dx. So for example, if we have y squared and we want to differentiate this in terms of x, we would just get the differentiation of this, which will look like 2y multiplied by dy over dx. And this is all of the content for differentiation for year 1 and year 2. So now let's quickly recap. So if you have terms added up separately, what you would do for differentiation, so say you have a function where you have terms added up like this, is equal to y. If you want to differentiate this, you would differentiate each term separately. Now, the second point would be to, if you have a constant term in front of the differentiation, you can just do the differentiation and take it out. So if you have a constant in front of a function of x is equal to y, you can just take out the constant and only differentiate the inside to get dy over dx, and keep the constant multiplied on the outside by the by the new differentiated form. So you'll get a f dash x is equal to dy over dx. Then 3, if you have a composite function, use a chain rule. So a composite function will look something like this. If you have two functions multiplied by each other, so f of x times g of x, use product rule. If you have one function divided by another, f of x over g of x, for example, use quotient rule. And 6, if you have x, y on same side, use implicit differentiation. And this all worth noting as well that when you differentiate any function, f of y is equal to g of x, for example, or in terms of any of them, when you differentiate, even if it's just y on one side, so you have y is equal to g of x, you are actually differentiating both sides. So it's worth noting that. So we get dy of dx is equal to g dash of x. And that's the end of the video. Thanks for watching. I hope this was useful for you.